So yesterday we talked about adding fractions. In grade 6 you added fractions that had common denominators, and it wasn't very tricky. In grade 7 you were given two fractions, and in order to add those fractions you had to modify one of the denominators so that they match. Remember our conversation that the denominator tells you what it looks like, the numerator tells me how many there are. It's how many there are. The numerator tells me how many there are. The denominator tells me what it looks like. Okay. You might have got mixed up with that because I kind of said it a little bit backwards from the way that we normally say it. Be flexible. Be flexible. So then we looked at some more advanced fraction addition where I have two fractions that both have to be changed. I'd call that a bit of an advanced problem. And we're not talking about mastery. We're talking about just the level of difficulty of the particular problem. Can you get through it will then determine whether you're proficient with that concept or mastery with that concept. So today, we're going to be talking about, you guys all have sheets in front of you, the big idea of what we're going to be talking about today is to be able to recognize when two fractions actually say the same thing. We're going to take a fraction, and in order to change denominators and change the way that we look at things, we need to be able to create things that we call equivalent fractions. There's a word inside of equivalent. What's the word in there that tells me what it means? Brooklyn. Equal. Beautiful. Equal. Even though the L's way over there, equivalent means equal. Two things are equal. So, this is last lesson we converted between mixed numbers and improper fractions. In fact, we actually haven't done that just yet. We'll start working on that today/tomorrow. There's two different ways to represent the same quantity. So if we take a look at this, if I say I have one whole, maybe I take that one whole and I chop it up into two pieces. I now have two halves, right? That's what this says right here, two halves. I take one whole, I chop it into two pieces, I have two halves. Have I changed how much I have? No. But I've changed what they look like, what the pieces look like. I now have two pieces instead of one piece. I have two pieces, but they're halves now. I change how many I have, and I change what they look like. I could take that whole, and I could chop it up like this. I now have 3 thirds is the word. Very good. I have 3 thirds. These look different than each other. Okay? 3, numerator, how many I have. Denominator, what that piece looks like, or how many make a whole. Okay. I could chop this up into 10, and holy chamolies, would that be a pain in the derriere here? How would I do that? I'd have to go choppy, 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 choppy in such a way that all of the pieces are the same size. That's not probably tenths right there, but I don't make me do that. And I could chop that whole into 10 pieces, and each piece would be a beautiful 10 over 10. So 10 divided by 10 is 1. 3 divided by 3 is
1.
2 divided by 2 is, what's the difference between all of these things?
They just look different, but they're the same.
They are the same, it's just the way that I'm choosing to look at them. Okay? They all say the same thing. I could have a loonie, I could have 100 pennies. It's the same amount, but it's different. It's the same but different. Wow, is that confusing?
No.
Okay, good. I'm glad. Okay, let's see if I can scroll down here. So, if we look at our manipulatives from the other day, we're going to explore this. If I look at our manipulatives, remember we painted and colored and cut out a piece that looked like this. This represented the half of a whole. So the whole looks something like this. Oh boy, that's horrible. Anyway, use your imagination. And we chopped it in half. So notice, I don't have a whole here. I have one piece of the whole that's been chopped in half. I have one of a half of the whole. And there's what it looks like. There's the piece that's right here in front of us. Notice, I could take this piece and I could break it into 3 separate pieces. Now it's very important that all those pieces be the same size. So I could cut this into separate pieces where each piece now would represent not a half, but 1/6 of the whole. Each piece is 1/6 because I need how many of those pieces to make a whole? Good. I had a half, and I've chopped that up into 3 pieces. Where'd it go? Down here. 3 pieces now. 1, 2, 3. And they are these little triangles, just like our little manipulatives that we had. These little triangles, which we call 1/6. And I have 3 of the 1/6. Okay. Whoa. Oh, I gotta change this. This is too hard to manage. Okay, I think here we are. We could also take this, we've chopped it into 3s, but I could take that and I could chop those into 2s. I'm gonna take the 6th and I'm gonna chop it into, what would the 1/6 piece turn into?
1/12.
1/12. Very good. Because when I chop that piece off, how many of these does it take to make the whole?
12.
12 of them. So I could take the 1/6, cut it in half, and I create pieces that look like 1/12. I'm changing the denominator because I'm changing what the pieces look like. I'm changing how many pieces make a whole. Once we practice this, you'll be like, oh yeah, Kat, I know what's going on for sure. Now, if I took a half, or I took the 3/6 and I cut all of those into 2 pieces, into 12ths, how many 12ths do I have? 1, 2, 3, 4, 5, 6. I have 6 pieces cut into 12 that were cut into 12ths. 1/2, 3/6, 6/12. Notice the top number is always just half of the bottom number. Because that's how many I have. I still have half of a whole, half of a whole, half of a whole. Okay, we'll talk about the math, because right now all we're doing is taking some pieces and we're snipping. Flip the page, please. Let's take a look at this example. We're flipping the page.
Okay.
Remember your manipulatives. What fraction do I have right here on the board? What is this right here? This board is so sensitive. Go ahead, Station.
2/3.
Good. How many would it take to make a whole? It would take 1, 2, 3 pieces to make a whole. So each piece is a third. I have a third and a third, which makes a total of 2/3. Wow, mind blowing. So here I have 2/3. I'm going to take each of these pieces and I'm going to cut here and here. I'm taking each third and I'm cutting it into 2 separate pieces. How many total pieces do I have right now after choppy choppy? Madison?
2, 6, 2/4.
I have 1, 2, 3, 4 pieces. 4 goes in the numerator. Excuse me. What's the size of each piece? How many pieces would that now take to make a whole? How many pieces would it now take to make a whole? Marcus.
In total, it takes 6.
Perfect. I need 1, 2, 3, 4, and then I would need one down here for 5 and 6, and that would be a whole. So I have 4 pieces like 1/6, little triangles, like our manipulatives. I could take that again, and I could cut those pieces in half, just like we did earlier. How many pieces do I have now?
Oh, sweet Jesus.
Please. That's being recorded, right? Thank you. Josh, how many pieces do I have now? No. You just counted them. How many do I have in total? There, in front of me. How many pieces? Yes. Good. I have 8. And how much is each of those pieces worth of the whole?
The whole would be 12.
It would take 12 of them to make a whole. That's right. Notice I'm still missing 1, 2, 3, 4. 4 and 8 would give me the whole, which would be 12. So 12 pieces to make the whole, and I just have the 8. What if I now, we're not going to look at these pieces anymore, but you should see a trend. Every time I cut all my pieces in half, what happens? Okay, this is turning crazy. Hold on. Yeah. Every time I cut my pieces in half, I took my pieces, I cut them in half. I took my pieces, I cut them in half. I took my pieces, and I'm going to cut them in half again. Every time I cut in half, 2 things are happening. The top, the numerator, I double how many pieces I have, and it takes twice as many pieces to make a whole now. I'm not changing how much I actually have. They're all equivalent. I'm changing how I'm looking at all the pieces. Very good. Very good. So, if I cut it in 2 again, what do I get? Thank you. If I cut this into, I don't need pictures now. I should be able to follow the trend.
16 over 24.
Perfect. 16 over 24. What if I cut it in half again?
32 over 48.
Perfect. 32 over 48. An interesting question last year, somebody said, why are we cutting it in half and multiplying it by 2? Doesn't cutting in half mean dividing by 2? Good question. Why is it kind of the opposite of what we think is going on?
Because when you cut it in half, you're not taking away anything, you're just making more.
That's right, we're just making more of them, and they're getting smaller, so we need more of them to make a whole. That's why the denominator keeps getting bigger and bigger and bigger. As the pieces are getting smaller, I need more pieces to make a whole now. As I have a certain amount of something and I'm dividing it but not getting rid of, just cutting it into 2 pieces, I'm creating more and more and more and more and more and more. So my numerator goes up and up and up and up. These say exactly the same thing, it's just a different way of looking at it. Okay? Notice again, we're not changing how much we have. Better nose for this because it's not working there. Notice we're not changing how much we have, we're just changing how we look at it. Good. When we use manipulatives, that's what we call concrete mathematics. That's with your hands on it and you're moving things around. If I said, build me a shed, that's concrete. Sure, it's carpentry, but there's a lot of math that goes along with measuring things out and cutting things and making sure that it's going to sit up straight and not fall over. If we do something with pictures like we did here just a little while ago, we call it pictorially, so that you can represent what's going on using pictures. Okay? Concrete, pictures, and then using symbols. Symbols just means just doing the math, using numbers. Okay? So, every time we cut the piece, we are increasing how many pieces and increasing how many we needed to make the whole by the same factor, in this case 2. So we were talking about that. Now we're just going to look at it symbolically. If we take a half, like we did at the very beginning, and we cut it into threes, notice what we did, and as Danny mentioned, we multiplied the top and the bottom. If we're cutting it into thirds, then we're tripling how many we have, tripling how many we have, and also tripling how many it takes to make the whole. We multiply the numerator, and we multiply the denominator by 2. Sorry, 3. 3 in this case. If we took that and we cut pieces in half, cutting in half is now doubling how much we have. So, 8G. They were here last week. Yep. Okay. So when I double, I'm doubling how many I have. If I had 3, I chop those in half. I now have 6. If it took 6 to make a whole, and they're half the size they were before, now it takes 12. So I multiply the top and the bottom by 2, and I get 6 halves. We've done that in example number 2. The one that we all did together. I had 2/3, and then I chopped those pieces in half, and I created sixths. So 1, 2, 3, 4 sixes when I cut it in half, and I'm doubling by multiplying by 2. I create more by cutting things in half, but each one is smaller. I've said that like 10 times now, eh? It's not like a broken record. Again, we cut it in half again, and we get 8/12. And we could keep cutting, and we could keep cutting, we could keep cutting, we could keep cutting, and they get smaller and smaller, but I get more and more and more of them. And I need more. Okay. Let's look at some straight up examples. If I had a fraction 2/5, so we're on the bottom of the 3rd page now. If I had a fraction that was 2/5, and I needed to change it to what we call the equivalent fraction, where the denominator is 10, what did I do to convert it from needing 5 pieces to now needing 10 pieces? What did I cut it into? Bingo. So if I had 2 of them, and I cut everything into 2, I now have how many pieces, Brett?
10 pieces and 4 on the top.
I have 4, and I now need 10 of those to make a whole. Very good. So to get from here to here, I multiplied by?
2.
Therefore, I'm going to do the same thing up here, and as Brett says, 4/10 is the same as 2/5. Okay, change the fraction 3/8, so the numerator is going to be a 12. Alex.
So if you multiply it by 2, you get 6 and you get 6 and 16. And then if you subtract by 4, that will give you the answer.
Okay. What you did in your first step was not wrong. You're going the right direction. Okay? You're going from 3 up to 6, but we want to keep going until we're at 12. So let's kind of cut out the middleman here. When we're changing fractions, we're not taking pieces away and putting pieces in. We're going to multiply or divide only to change those fractions. It's the only way we can change the fractions to an equivalent fraction is by multiplying. So your first step was on the way, Alex. I liked what you were doing. But let's do it all in one step. If I had 3 and I wanted to multiply by what number to get 12? Zach? 3 times what gives me 12?
4.
Bingo. So I'm going to take my 8 and I'm going to, Anna?
Multiply
By?
4.
Awesome. Multiply the top and the bottom by the same number, and I get 32 in the denominator. 12 in the numerator, 32 in the denominator. Good. We can also use this to go backwards. We can make our equivalent fractions bigger, but we can also, as we started to practice the other day, take big fractions and reduce them. To make them bigger equivalent fractions, I multiply, and to make them smaller, I'm going to bingo, the opposite. What if multiplying is going in there with a pair of scissors and cutting them into smaller pieces? What would dividing be? What would I be doing with the pieces if I was dividing?
Erasing the cut.
Erasing the cut, or like physically, what would I have to be doing to
Maybe
them?
like take them away or take them out.
But if I took them away, then I'm changing the quantity. We don't change the quantity, we change how we look at them. I would be,
Putting them back together.
yeah, or I'd be taping them together or stitching them back together. You know, insert a verb here. I'm taking small pieces and I'm putting them back together. The opposite of cutting them. Okay, very good. So in that last example, that's what we see here on the back page, the top of the back page. We have a big fraction, 10 over 20, and I'm going to reduce it as much as I can. So we look at what can I divide the top and the bottom by. Let's look at what multiplies to give 10. What multiplies to give 10?
5.
And
2.
good. Look at that, I already have the answer, don't I? 5 times 2, and to get 20, I multiply. Yes?
2 by 10.
Oh, Peter. 2 times 10. So what can I divide the top and the bottom by right now? Yeah, I can get rid of this multiplication by 2. If I divide the top and the bottom by 2, I'm getting rid of the multiply by 2. What's left? 5 over 10. Now notice my question here. Is that the lowest possible fraction?
No.
What else can I divide the top and the bottom by to make it even smaller? What divides 5 and divides 10? 5. 5 divided by 5. How many 5s fit in 5? 1. So if I divide by 5 again on the top and the bottom, I get 5 divided by 5 is 1. 10 divided by 5 is
2.
2. 2 5s fit inside of 10. 2. So, is this the lowest possible fraction? No, I can go all the way to a half. Okay, we have some examples here. Try those out for me, please. There's 3 examples at the bottom of the sheet. Okay, let's have a fit. 4 examples, pardon me. There's 4 fractions. Let's just practice reducing those to lowest terms, please.